Hello, today we're going to be talking about finding empirical formulas, what empirical formulas are, and how we can solve for them given experimental data. So first of all, you should be working off of worksheet B. You should have that in front of you while we're doing this, and you'll be working through some sample problems with me, or I'll be working through them with you. You should write down exactly what I'm writing down, and then you have some examples to go off of when you finish the rest of the worksheet. So first of all, empirical formula is a formula that gives us the lowest whole number ratio of atoms. So for example, if I look at the formula for H2O, that's water. There's 2 hydrogens, 1 oxygen. That can't be reduced down any lower. That is the empirical formula for H2O. We know that like our ionic compounds, we had talked about the way we write those formulas where the charges add up to 0, but we need the lowest whole number ratio. We've seen that mentioned before, lowest whole number ratio. So all of our ionic compounds actually automatically come as empirical formulas. So for example, if I have calcium sulfide, well, calcium's +2, sulfide's -2. I don't write Ca2S2, right? I don't do that. The lowest whole number ratio that I need for the charges to add up to 0 is just 1 of each. Okay. There are some organic compounds or non-ionic compounds or molecular compounds. For example, hydrogen peroxide. Its formula is H2O2. So notice that both H and O have a factor of 2 in common. So the empirical formula would be reducing down the subscripts. And so that would reduce down to HO. And this then is referred to as the molecular formula. So we're going to be looking at finding molecular formulas as well on the back of worksheet B, but a molecular formula is basically, we know the word molecule specifically refers to a covalent compound, but it is the formula that has the actual number of atoms that make up the compound. So obviously H2O2, its real formula is not HO. There's 2 H's, 2 O's bonded together, gives it the properties of hydrogen peroxide that we're familiar with. But again, it is not the lowest whole number ratio, and we've seen that with molecular or covalently bonded substances, that they don't have to have the lowest whole number ratio formula. So we refer to that formula, whatever the real formula is, as the molecular formula, and again, really that's referring to covalent compounds. The empirical formula is the reduced down form. So if there is a subscript, if there's a factor in common of all the subscripts in the formula for the compound that you can reduce them down by, then that's what you should do. So again, this is already an empirical formula. This happens to be the molecular formula for water. Cannot be reduced down any further, so it's molecular formula. And empirical formula happen to be the same thing. In any ionic compound, they automatically come as empirical formula. But again, it's that lowest whole number ratio of atoms making up the formula. Okay, so let's take a look then at finding an empirical formula, because that's really, if I have experimental data, and we know that in lab, I can't measure numbers of atoms. What I can do is measure masses of a group of atoms, and I can relate that to the number of atoms based on the concept of mole that we've talked about. So looking back at water, we know from what we talked about at the beginning of the year that we figured out that when we always have, so this is according to the law of definite proportions, we always have the same mass ratio of hydrogen and oxygen, so the same mass percents making up the compound of hydrogen and oxygen that we've got water, that we will have, the properties of water, the density of 1 gram per milliliter at 25 degrees Celsius, that we will have, the specific heat of 4.18 joules per gram times Celsius, et cetera, et cetera. So we related that using Dalton's atomic theory to the fact that we always have the same mass ratios making up compounds because we always have the same formulas or the same number of atoms making up a compound. And so what we're doing is trying to take mass data, which is what we can measure experimentally, and trying to figure out what would the formula be. How many H's does that come down to? How many O's does that come down to? How many of whichever atom does that mass or mass percent relate to in an actual formula? So that's what we're looking at here today. So on worksheet B, you've got the definition of empirical formula. You've also got the steps that we're going to be working through. We're going to go through 2 example problems together, and then you're going to do the rest of them on your own for your homework. So write down the detailed work of the examples that I'm doing so that you have it. Okay, so let's look at the example problem. Notice we're given masses to start with, so that's very common, right? If we were in lab, we would be able to measure, maybe be able to figure out okay, how many grams of this element ended up in our compound, how many grams of this element ended up in our compound. And we will do this experimentally, actually, at some point in experiment. We also have done the example with the candy, where you can see we measured masses, related that to the number of pieces of candy we had in the bag. So let's take a look here. So 13.29 grams, labeling everything is very, very important. So I am labeling, actually I'm going to start writing over a little bit further. 13.29 grams, and I'm labeling that as potassium because I need to pay attention to which elements I'm dealing with, because obviously eventually I'm going to be trying to write a formula, and I need to know which molar masses to use and so forth and so on. Okay, so 13.29 grams of potassium, I have 17.68 grams of chromium, and I have 19.03 grams of oxygen. Okay, so step one on our sheet here says, if given a percent composition, assume a sample size of 100 grams, and that way the mass is the same as the percentage expressed in grams. So these are not percents, these are just grams. So we're just going straight into step number 2, which is we're taking our experimental masses. And again, if I want to try to relate, well, how does this relate to the number of atoms that appear in the compound formula? Mole is the way that we count atoms. So my first step is to convert to mole. So if you remember why we're doing what we're doing, that's pretty important here. So I'm looking up the molar mass. So that's why I labeled this. This is grams of potassium. So I want to look up the molar mass of potassium, which is 39.1 grams. So there's that. Again, it's times the numerator divided by the denominator, and what I get is 0.3399 moles, and that is potassium. I'm going to keep that labeled. Notice this has 4 significant figures. I want to keep at a minimum at least the number of significant figures in my original number, and maybe for these problems even an extra digit or so, because this isn't our final answer. But if we round too much too early on, it might actually make it harder for us to get a logical, nice answer. So we want to, at least at a minimum, keep the number of digits that we started with, if not more. So just don't chop off numbers. It's really going to wreck things. Okay, so for the chromium, we've got 1 mole divided by, so the molar mass of chromium is 52.0 grams. And when I divide that out, this actually comes out to a square 0.34. And that's it, like that's all your calculator will give you. I'm just going to throw a couple extra zeros on here just to show me that that's, 0.34, period. And then for oxygen, the molar mass of oxygen is 16.0 grams. Again, I'm coming up with all of these numbers out of the periodic table. Okay, so you should go and double check and go find the CR, so that's in the transition metal section. Its molar mass is 52.0 grams. Oxygen, molar mass is 16.0 grams. And so I get 1.189 moles. So I have found moles for each of these things. Now, my objective with finding moles is that this represents the count, the relative number of particles of potassium, chromium, and oxygen. So my overall goal here is to come up with the formula, right? Empirical formula is, well, what's the ratio, what are those subscripts on my elements? And if you look at what we found here, so this is the ratio of the particles. So if I write those in as subscripts, well, the problem is that we don't use decimal numbers as subscripts. So we need to come up with a way to make these numbers into whole numbers. Okay, so the best technique for that is what's mentioned in number 3. So you're going to divide the number of moles. So each of these is the number of moles for each element by the smallest number of moles. So if you look through our numbers, well, these two numbers are practically the same thing, right? 0.3399 is pretty much the same thing as 0.34. So we're going to divide all 3 of these numbers by the same number, right? Because we're coming up with a ratio. We're trying to come up with a whole number. This is actually the fastest, easiest way to do that. So this is my smallest number. So what we're going to do here is step number 3. We divide everything by this smallest number of moles. Now notice if I'm dividing moles by moles, the units are actually going to cancel out. So there's not going to be any units on this number. And that's okay, because we're just looking at the relationship, the ratio between the numbers of each type of atom. All right. So with this, well, dividing something by itself, we get 1. Again, you should be trying this on your calculator to make sure that you can see where these numbers are coming from. This number, and it's pretty much the same number, so that's pretty much 1.189 divided by 0.3399. So that gives me 3.499. Okay, so this is kind of close to 3.5, right? 3.499, that's pretty much 3.5. So right now, the way this looks is instead of these crazy decimals, now I've got a 1, and a 3.5. Well, you still can't have a 3.5 as a subscript. Okay, and actually this formula should be written closer together. I just have them written kind of far apart because of the size of those subscripts before. And again, technically we don't write in ones. Okay, well that still isn't adequate because I have a decimal here. So notice step 4. The ratio is near a whole number within 0.1 then round. Well, this is a whole number, this is a whole number. 3.5, well that's not close enough to round up or down, right? It's not close enough to round up to 4, it's not close enough to round down to 3. So what we're going to do is, well, how do I make something that's 3.5 that has a half, a whole number? And so what I can do is multiply that by 2, right? So if something has 3.5, something is 3.5. If I multiply that by 2, well, whatever I do here, again, since this is the ratio of the number of atoms, I need to do the same thing to all of my ratios. I think I'm kind of almost off the board now. So notice by doing that, I have 2 potassiums, I have 2 chromiums, and this gives me 3.5 times 2, that would be 7 oxygens. So my formula, and this is my final answer, so the whole reason we've been doing this is to come up with this thing. This is the empirical formula. So this tells me that I have 2 potassiums for every 2 chromiums for every 7 oxygens, right? So these numbers that I came up with, I converted masses to moles, which represent number of particles, and I'm using that ratio of number of particles to come up with my formula. Okay, so that's one example. Now let's go through another one where we are dealing with percents. So we're going to go through practice problem number 1 with manganese and oxygen. So notice instead of being given masses, we're given mass percents. And so the only difference in how you're getting started is listed in step 1 on your sheet. And it says that if you're given percents, if we assume a sample size of 100 grams, let's see what that would look like. 100 grams is my sample size. And if I have, where are we at here? 69.6%. Well, we know that 69.6%, before we work with that in mathematical equations, we need to convert a percent back to its decimal form. So we know that percent means per 100, that's the cent means 100. So this is 0.696, and this, then if I have 0.696 or 69.6% of my 100 grams, that means 69.6 grams. So you don't have to have all this written down as your work. You don't ever have to do this again. Just recognize that the reason we're picking a 100-gram sample is we're just given percents. We just need some mass to go off of. And so literally, if I pick 100 grams, I can take the percent. So notice this number that I came out with for grams of manganese. That's exactly the same as the percentage that I started with. So that's why I'm picking a 100-gram sample in the first place. Okay, so for setup, I'm going to start manganese, and notice how I'm doing all my calculations in a nice, straight, neat line, so that I can keep track of everything, what goes to what. Okay, so 69.6 grams of manganese, and then we've got 30.4% of oxygen, so 30.4 grams of oxygen. All right, so converting to moles, so we look up the molar mass of manganese. So manganese is not the same thing as magnesium, and that is 54.9 grams. That's a transition metal, and so we end up with moles of that, 1.268. Notice I'm keeping at least an extra digit here, just to avoid any rounding errors. On this one, we've got 1 mole divided by, so again, oxygen determines the molar mass that I'm using here. This is grams of oxygen, so I use the molar mass of oxygen, and that gives me 1.9. And again, that comes out exactly on my calculator, so just to remind myself that I'm okay with significant figures, I'm going to write that extra zeros on there. Okay, so this was step 2, converted mass to moles. Step 3 now, picking the smallest number of moles. We want to come up with a ratio because I cannot use these as my subscripts. I need a whole number. So this is the smallest of the two numbers. Okay, so something divided by itself is 1. This number divided by 1.268 gives me 1.498. So notice that's pretty much like 1.5. Okay, that is not close enough to round up to 2, nor is it close enough to round down to 1. So far, my ratio is MNO 1.5. That's what these numbers represent. But I can't have a 1.5. So how do I get this to be a whole number ratio? Well, again, if I multiply these numbers by 2, so how I would pick which number to multiply by, well, that's actually given under 4a. So notice if it's a half, I'm multiplying by 2. If it would be 0.33, I would multiply by 3. That would give me the nearest whole number, and so forth. So I multiply these by 2. That gives me 2 for the mn, and 1.5 times 2 gives me 3. So these subscripts would be mn203, and this would be my final answer, my empirical formula. So there we go. So you're supposed to work through the remaining problems, 2, 3, and 4. So follow the steps. And again, our objective is to find this, the formula with subscripts, whole number subscripts. So when you're looking at your answers, make sure that, well, they should make sense, right? So I'm not going to have some crazy, like we haven't seen, you know, something with a subscript of 20 or 85 or 200 or something crazy like that. So, you know, the number should make sense. You know, manganese oxide, we've seen, yeah, this is in the realm of possibility of subscripts. So just make sure your answer kind of looks like it makes sense. And again, make sure you're using the correct molar mass. So by labeling this is manganese, I use the molar mass of manganese. This is oxygen, use the molar mass of oxygen. I'm keeping track of everything because I know that this number at the end of this line, that's going to tell me the subscript of manganese. All of these numbers from this line are going to tell me the subscript of oxygen. So if you're not keeping track of things, because you're all over your paper and you can't figure out what work goes with what thing, it's going to be very, very difficult to come up with, well, which number then tells me the subscript of each substance. So just being careful, being neat, that would be my advice to you. So we will take a look at molecular formulas next, and again, you're going to work through problems 2 through 4 on this worksheet.